Okay, Professor there, can we start?
Thank you so much. I greatly appreciate this opportunity to speak to you all about dairy products. And those of you who want a copy of this presentation, the easiest way is to use WeChat. And here's my ID. Write me and I'll send you a copy of this presentation. Or here's my email address. So let us then begin. And let's see if I can. How do I make this go? Oh, my. Here we go. That will make it go forward. And of course, this picture is incomplete from my viewpoint, maybe not from yours. And my question in this lovely picture here is, where's the ice cream? We're going to see all these different dairy products that are involved here. And we'll go through some of them. Okay. And here are some interesting facts. With over 90 billion US dollars, that's about 572 billion renminbi in revenues, and nearly 28 million tons of products consumed in 2020. That's for which I have the data. China is the world's second largest dairy market after the United States, and the world's largest one by dairy imports. And I tell you, this fact is amazing. This fact is rather amazing because about 92% of the Chinese population is lactose intolerant. So this seems to be absolutely contradictory, and yet it's true. And we'll examine this, and we'll go through this a little more as to what it all means. And so it is just one of these things that boggles my mind. Okay, we'll continue. So this is going to be about what, of course, we have to start with neonine, right, with milk. And I'm going to also talk about ice cream, which is very popular. Milk is a basic nutritional component of all mammals, providing nutrients, okay? Indeed, it is the first food that generally anyone first encounters is milk, often mother's milk. Here's an electron, here we go. These are electron micrographs of milk globules above and whipped cream to the side. And this electron microscopy of whipped cream showing is here the air, and F, okay, are fat globules, and then B is the internal structure, okay, of air bubbles, highlights the partially coalesced fat. And here's interaction of fat globules within the fat layer. And okay, so we see where this comes from. We have some good understanding of this. So as I say, humans are mammals, a word that means creatures of the breast. And the first food that any mammal tastes is milk. Milk is a food for the beginning eater, okay? A drinkable essence created by the mother from her own more variable and challenging diet. When our ancestors took up dairying, they adopted the cow, the ewe, and the goat as surrogate mothers. Okay, so here's what goes on. We are completely helpless for months after birth, while our brains finish growing to a size that would be difficult to accommodate in the birth canal, in the womb, in the birth canal. In this sense, milk helps make possible the evolution of our large brain, and so help make us the unusual animals that we are. We don't think about that often, but I'll show you this is really so. Okay, I thought I'd stop here for a moment and share with you a strange English lesson. An English lesson which I claim if you talk to most people who speak English, they don't know. Ask them, what do you think the origin is? Where did the word lady come from? And they look at you blankly. Well, it comes from day, and it's an old English day, female servant, and is the second part of many surnames such as Faraday and Doubleday. Doubleday means a servant of doubles, meaning a servant of twins. It forms the first element of dairy. Now we see the relation of dairy and lady, and the second element of lady. By the 1200s, the word lady referred to women whose major job was milking and making butter and cheese. So they were referred to as ladies, or we would also say dairy maids. today. Okay. Later in the 1900s, lady would become the female opposite of a gentleman and take on a much more glorified meaning. Okay. To be lady and to be ladylike. Very, very, very different. So that's, I think, interesting in terms of the background. And of course, language keeps changing. Here's something about the compositions of various milks. Here, all these things. Here's human milk, so we see what it's like. This shows the fat amount, the protein amount. It's not that high in protein, interestingly. Here's the lactose. It's actually quite high in lactose. Okay, lactose, as we'll see, is a sugar. Here's the mineral content, and look, 88 is water. Wow, it's mostly water. Here's cow, and there are different types. The Holstein Friesian is the one that now is most preferred, but here are others. Here's buffalo. Buffalo is quite fantastic because of its high fat content, and it's very much prized as well, buffalo milk. Here's yak. Of course, you know yak from northern China, and goat, what it's like, and sheep and camel. Okay, camel rather low in fat. Okay, reindeer, horse, even whale. Amazing. Okay, quite amazing, I think, and we have some idea about it all as to what's going on. But notice again the high water content. So milk, to begin with, if you ask what's milk, it's mostly water, but it has these other things. We're going to discuss them. So what is milk? It's an emulsion of fat globules coated in protein, suspended in protein-rich water. And so here we go. The liquid phase is lactose, slightly acidic water. I don't know, again, the background of the class, whether you've had much about acids and bases. I'm assuming you know what pH is. And you better stop me if you don't, and I can explain. Anyways, and we have bundles of proteins, and then we have a fat phase. These are droplets of oil cased in protein, as we'll see. So here's milk. Here's the water part, aqueous. Here's the oil and fat part, with various things being said what they are. We're going to see more about this as we go on. Okay. And so let's look at it. Mostly water. That's what we said. And here it is being divided up. This is the non-protein nitrogenous compounds. That's NPN. Okay. And by and large, we're seeing here's the fat part. Here's the lactose. That's a sugar, as I mentioned to you. This is a protein called casein. This is the part that's called whey protein. It's soluble in water. Not so much. This is not. Okay. This is very little. Here are minerals, salts, vitamins, and enzymes. Okay. And particularly from your mother, antibodies, which are very useful to you when you're starting off. Okay. There's a picture of what milk is. And so we begin now with milk sugars, are primarily what's called lactose. Lactose provides nearly half of the calories from milk. And it's made from two simple sugars that has a glycosidic bond that connects them. This is the glycosidic bond. These are the different sugars. You notice sugars are carbohydrates, okay? Carbon, these are the carbon atoms, and then this is the OH and the H that's on them in this structure. And this particular half of lactose, this one shown here, is what's called galactose. And this is not the same as this. If you look carefully, you'll see differences. You can see there are differences as to what they are. And this one is called glucose. That's the sugar, simple sugar, glucose. This is galactose. This is really, these are monosaccharides. This is a disaccharide called lactose or milk sugar. Okay, so we're going to continue with lactose, as we're showing you again more here. Disaccharide, glucose, and galactose prepared as separate molecules condensed into milk sugar through the secretory cells. And the ability to digest, to metabolize, or break down lactose requires a special enzyme. This enzyme is called lactase. Okay, lactase is produced in gut by children but levels decrease in adults. People who start, all mammals start with having lactase, but the amount of lactase falls off in time, and it falls off depending upon your genetic composition more rapidly or less rapidly. Northern Europeans maintain levels, but only 30% of others can produce significant quantities. This is the nature of lactase, as we'll see. Okay, and I now want to talk about what people call lactose intolerance by group. So what is the trend of locations of people with and without lactose intolerance? And I'm showing you the percentage of adult population that can drink milk as much as they want. And look, see what's in white? Only it's awful. Look, and where are you? And you see where you are. You're right there. Okay. And yes, there's certain spots here, but look here in Northern Europe. There no problem at all. Very little. See, but it varies. And I'm just showing you this part to get an idea. And this is fascinating. What are you going to do about it? So I thought I'd start by explaining how China has overcome lactose intolerance, because it really has. And here I'm going to point to the Chinese government. It has played a really significant role in making this happen. It's promoted dairy consumption. How did they do this? In the early 2000s, the government launched a program aimed at providing each child with a cup of free milk at school. I bet those of you in China have experienced this, okay? That's one of the big drivers. And the truth is, once you start to drink milk, as I'm saying down here, drinking a cup of milk is not enough to cause big gastrointestinal problems. And by keeping up milk consumption, drinking milk, since being a child causes lactase production in the body not to fall off as rapidly as not having daily amounts of milk products. So it's very much related. The other thing is growing health awareness among consumers is another powerful driver to increase consumption. The idea that milk is really healthy. And finally, yogurt has gained in popularity in China, particularly with a recent estimate that 40% of Chinese public take yogurt at least once a day at present. So lots of yogurt's now being consumed. So what makes yogurt so popular is that it is low in lactose, which overcomes the lactose intolerance problem, and it's high in nutritional value. And then, of course, you can flavor it, so people love it. I happen to like yogurt too, okay? And there's various variations of yogurt, but enough, you get the idea. So what again is milk? Here we're showing you this thing again, and we've seen this before, and we've seen this glycosidic bond. If the sugar is not hydrolyzed, the sugar is transported to the gut where two things happen. If you can't break this bond, then the water rushes to the intestine from the belly, that's osmosis, and bacteria will start to metabolize, break down the sugar to form carbon dioxide and methane, CO2 and CH4. What's the result? You get cramps, you get gas, you get diarrhea. This is what happens to people who drink too much milk and who do not have lactase in their system. So this is called lactose intolerance. Today, though, enzymes are mass produced in pill form that can actually help people who suffer from this. Now, let's talk about actions of lactase. So this enzyme, lactase, hydrolyzes the glycosidic bond, breaks apart the glycosidic bond of lactose, producing these two sugars. So now we get the monosaccharides, which are consumed by further metabolism, and people are happy. So I've gotten now through lactose. So why lactose? Animals and humans use glucose as the main sugar source. Okay, talk about having an infusion. People often give glucose. Okay, second half of lactose is galactose, and it's used for neural tissue, things that build nerves, particularly the brain. So it's very important in early development of mammals. Now, turns out that most bacteria cannot digest lactose for 1 or 2 days. means that it's a safe time for contamination-free milk to be consumed. You don't want to leave milk out unrefrigerated for more than a few days. And when bacteria start to work on it, it breaks it down. And you also get not only this, but you also get lactic acid formed in the milk, and it becomes sour. You get sour milk. Okay. So here we go. More composition of milk, liquid phase. Now we're going to turn to proteins and talk about something called curds and whey. Here are the different milk proteins. And let's step into this. Here's the different caseins. And I won't go into this in much detail. These are now the acid-soluble whey proteins. This is the stuff that easily goes in solution. These are acid-insoluble. Okay, remember that the milk itself is a little bit acidic. So thousands of proteins divided by their stability in acid. Unstable proteins which denature in acidic solutions bind to each other. They aggregate or coagulate. When you actually add acid to milk, now how would you do that? Well, the simplest ways we'll talk about is to add like lemon juice or lime juice or vinegar. All those are acids, right? Acetic acid from vinegar. You get the milk to curdle. These form what are called curds. When milk curdles, let's ask ourselves, what is happening? First, I want to show you a picture. Here's some pictures of curdled milk, and here's cottage cheese. That's its name we give it anyways. I think somebody used to sing this, and this goes back, I think, to some nursery rhymes, which all English-speaking people learn as children. Something about Miss Muffet sat on a tuffet. Tuffet is an English word for bushel of hay. And along came a spider and sat down beside her and scared Miss Muffet away. Okay, so that's a nursery rhyme to learn. And she was, Miss Muffet was sitting on a tuffet, curds and whey. I'm sorry, I didn't say that. So she was eating curds and whey. That came from this coagulation. And so now let's turn to the protein. Here's casein. And we see charged head groups, and these are hydrophobic core. Okay, this is water all around. These charges love water. They're hydrophilic, loving water. This is hydrophobic. They want to get out of the water, and they all cluster like that. Okay, so they mark globules. So this is the major single protein produced in milk. It's called casein. It's heat stable. It's a well-folded protein. It floats in what's called a micellar form, globs of protein arranged to keep the protein in solution. These are still in solution. Okay, this is from the acid-insoluble caseins, like so. This is our curds part. This will be those that are soluble. There will be what's called whey. Okay, more about casein. So we're looking here. We're seeing this. We're seeing here phosphate groups. Okay, this is the phosphate calcium casein bridge. So it's going to hold calcium. Heat stable, well-folded protein floats in this micelle form. Globs of protein arranged to keep the protein in solution. Hydrophobic portion of protein in milk. Calcium binds tightly to the protein, helps to carry calcium into the bloodstream system. And why do we need calcium? Well, quote unquote, it builds strong bones, right? So it's very important. There are four main forms of casein. One, and I'm not going to go over which is what. One caps micelles, limiting the size. At pH levels above 4.5, proteins are negatively charged and repel each other, right? Things of the same charge get out of each other's way. Those of opposite charge attract each other. It's going to be an important idea. When the H plus concentration increases, that means the pH is lowered. pH goes down. Remember, pH is the negative logarithm to the base 10 of the H plus concentration. The proteins denature. They unravel. They were globbed all together. Now they unfold. And they're not charged, and thus they bind to each other and curdle. In fact, we'll go more over how that curdling happens later. Okay, what about whey? I talked to you about curds. Now we can talk about whey. The other protein found in liquid phase of milk. It stays in solution in acidic conditions. And many of these proteins are what are called immunoglobulins, antibodies for the young animal, young us too. Lactoglobulin has several sulfur atoms, provides flavor and odor to cooked milk. Okay, sulfur often is involved in making odor, and you'll know that from H2S, and you also know it from onions, which again has sulfur in them. The odor, very much sulfur is an odor thing. Proteins in whey are used for animals as a source of nutrition. And I'm telling you, we use whey as well. Some people think, oh, I'll throw it away. It actually, if you save it, you can use it wonderfully in gravies and making other dishes. And under more extreme conditions, whey proteins can form small clots. And this is what causes people to make something called ricotta cheese. These proteins help make ice cream creamy. Okay, the whey involved. Very interesting. And we'll look more into that. Okay, now I thought I would turn to 2008 and what's called, at least I call it, the Chinese milk scandal. And here's what happened. The Sanlu Group, I hope I say it right, okay, which was owned about 43% by people in New Zealand and otherwise in China, they added melamine. Now here's melamine. See the structure of melamine? They added it to milk. Why did they do that? Look at all the NH2s and the nitrogens in melamine. The idea was to increase the nitrogen content of diluted milk. So you can dilute milk. That means add water. Water's already water. Remember, milk's already plenty of water. Now add more water. And so it gives it the appearance of a higher protein content, allows people to sell it, even though you've watered down the milk. Now, the idea was actually a very clever one, but disastrous. Look at the nitrogens. It starts to make a lot of sense. And NH2, if again, you know about proteins with amino acids, NH2 groups, the amine group, all makes great sense. But these, unfortunately, in the body form kidney stones and worse. About 300,000 affected children were identified, and among which 54,000 were hospitalized, according to a report in 2009. And it's thought that 6 babies died from this contamination. So horrible, okay? You don't want melamine in milk. Drink it. Bad idea. Very interesting idea, but bad idea. Wrong chemistry, okay? Not understanding a side effect. Sounded brilliant, but it wasn't at all. Now, I want to turn next to a thing that's very popular, particularly in China, and that's powdered milk. Okay, powdered milk is also called milk powder or dried milk or dry milk, and it is a manufactured dairy product made by how? Evaporating milk to dryness. Evaporate means we heat it up and drive off the water. We get it powdered. Marco Polo, who visited, as you know, China, wrote of Mongolian troops carrying dried milk in the time of Kublai Khan. So this is very clever. Milk weighs a lot. If you get the water out of it, it weighs, you know, something much less, right? Many times less. And so this makes a lot of sense to take powdered milk if you're going on a big trip and then add water to it later to make milk back up. So in modern times, pasteurized milk, and I'll explain pasteurization in a moment, is first concentrated in an evaporator to approximately 50% milk solids. And the resulting concentrated milk is then sprayed into a heated chamber where the water almost instantly evaporates when it hits the walls of the hot chamber, leaving fine particles of powdered milk solids. And interestingly, powdered milk has the same nutritional value as whole milk. So the process is done without being so hot that it destroys anything. It doesn't cause us to lose a number of the nutrients. So it's particularly useful in preparing baby formulas. So powdered milk's been used all the time in baby formulas. And I think that's true throughout the world pretty much. Okay. Okay, now comes cooking with milk. Much of the milk that we use in cooking disappears into a mixture, a batter or a dough, a custard mix or a pudding. It certainly can be used in making bread, making pancakes, making other things, whose behavior is largely determined by other ingredients. Okay, milk serves primarily as a source of moisture through the water, but also contributes flavor, body, sugar, and our lactose that encourages browning. I don't know if you've studied it yet, but you'll talk about the Maillard reaction, which allows sugars and amino acids to come together, and salts that encourage protein coagulation. The skin that forms on the surface of scalded milk, suppose you heat it a lot, soups and sauces, is a complex of casein, calcium, whey proteins, and trapped fat globules, and results from evaporation of water at the surface and the progressive concentration of proteins there. So that's what happens when you scald milk. Now, if you were to ask me about countries that stand out with regard to milk, the country that I would first point to is the Indian subcontinent, India's galaxy of cooked milks. And I tell you, anybody who's visited places, India, Pakistan, Bangladesh, etc., will understand this. So for sheer inventiveness with milk itself as the primary ingredients, no country on earth can match India. Its dozens of variations of the theme of cooked down milk, many of them dating back 1,000 years, stem from the simple fact of life that in a warm country, the simplest way to keep milk from turning sour, from souring, is to boil it repeatedly. Eventually, it cooks down to a brown, solid paste with about 10% moisture, 25% lactose, 20% protein, and 20% this butter fat. Even without sugar, what's called like a koa, is almost a candy. So it makes sense that over time, it and the intermediate concentrations that precede it became the basis for the most widely made Indian milk sweets, donut-like fried gulab jamun, and fudge-like burfi are rich in lactose, calcium, and protein. A glass of milk distilled into a morsel. So again, any of you had a chance to visit Indian restaurant and try these, this is what you expect. Very sweet. This is very much a dessert that people in India, and for that matter, the US like. However, in China, people do not like sweet things for the end of the meal. So culturally, this doesn't work, but you'll still find it interesting and you know now something about it. A second separate constellation of Indian milk sweets is based on concentrating the milk solids by curdling them with heat and either lime juice or sour whey. The drained curds form a soft, moist mass known as chana, which then becomes the base of a broad range of sweets, like porous, spongy cakes soaked in sweetened milk or syrup. This is the rasmalai or rasagola. So you get some sense of where some of this is coming from. That's one area that is amazing in terms of what it does to milk. The other area, which is truly amazing, and we'll get to later, is France. France is the country that I think beats all others in the number of different types of cheeses it makes out of milk. But I'm getting ahead of myself. Let's go on. Milk fat. Okay. The other phase of milk, okay, the non-liquid part of milk are globules of fat, which are mixed with many different kinds of molecules. Fats, the kind of fats and the amount of fat globules in milk vary as the types of food the cow eats, the season and the temperature of year, and the hormonal state of the cow. There's more fat in the milk in the wintertime and at the end of the lactation period. Mostly saturated fats and a few polyunsaturated fats. Saturated means that there are no double bonds. Unsaturated means we have double bonds. Carbon, double bond, carbon, these are in this. Fat-soluble vitamins. And this is very important that I should tell you this. Vitamins like very much to dissolve in fat. Okay, vitamins do poorly, as well as spices. Spices do poorly in water. You can't dissolve spices well in water in general, but you can dissolve them in fat. So people use butter all the time or olive oils, different oils to add spices in cooking. It's a secret of cooking. Remember, like dissolves like. That's the idea here. And water is not to be used for this purpose. But we'll go on. Here are now the structures of some of these. These are triglycerides. Tri means 3, and you can see the structure involved. Okay, milk contains about 65% saturated and 30% mono unsaturated. That means 1 double bond, and 5% polyunsaturated fatty acids, either free fatty acids or fatty acids bound to glycerol. Okay, and we can go through the nature of this. Here's a double bond that I'm showing you. I wish I knew better how much chemistry your class knows, so I would know better what to say. But you see, this is poly unsaturated. This is mono unsaturated. This is here just saturated, as shown here. And here is the glycerol molecule. And so we see how you get a triglyceride. People talk about this all the time. Okay. Fat globules with 3 layers of lipid membranes encase the triglycerol fat core. The serum phase with dissolved lactose and whey proteins contains the casein micelles coordinated with calcium ions. And I'm showing you a structure of milk. Again, what we know. And we'll run on to this. So here are the phospholipids and sphingolipids. And we can see here's the glycerol part. And this entire molecule is called a triglyceride. You see, these have these long chains. These are chains of fatty acids that have bonded glycerol. Okay, and they are acids that connected to this alcohol, forming an ester. That's what formed here. And this is now the phosphocholine polar group of atoms. Okay, this entire molecule is called a phosphatidylcholine. Okay, and here's this one. This shows you what these are, and so forth. Okay, I just want to get you so we know what we have. We understand what's in milk. The richness of milk, creams, or cheeses refers to the fat content. We say if milk is rich, it's because if it's fat content. The fat globule coated with protein and charged phospholipids, emulsifiers, creates charged spheres that repel each other. If globules were to contact, they would pull, resulting in a big batch of oil. But because they're charged, they stay away from each other. This formation protects by hiding the fat from the bacteria, which would quickly digest and eat the oil, the fat. Okay, now we get to the idea of pasteurization and homogenization. Okay, heat plus time equals sterilization. So subject food to enough heat to kill contaminating pathogenic bacteria, but not cook food too much. So you actually take the milk and you pass it through hot pipes, okay, that it indeed can kill the bacteria. And this is the basis for pasteurization or any kind of food preparation. High temperature, short time versus low temperature, long time, okay? There are other ways. You can do irradiation. Exposure to a small amount of gamma rays kills parasites, but like cooking, can alter food nutrient value, breaks other things apart too. But most common is pasteurization, coming from Louis Pasteur, okay? Now, what's this thing called homogenization? Homogenize means make it all the same, right? So left alone, milk will separate. Less dense, large fat globules float and pull at top, and more dense water later forms at the bottom. Now, homogenization forces milk while hot through small nozzle to break fat into small globules and gets it all mixed up and makes an emulsion that's stable. Okay, these become the same charges and they repel each other and it's stabilized. That's how we make homogenized milk. So more fat, smaller fat globules result in higher surface area, not enough membrane to cover fat, so casein will coat the fat. Smaller globules are less dense and repelled by casein, so on. And we can go through the whole thing. You can study this if you want to get a feeling for what's happening. So a lot of milk is homogenized, and it will keep that way. So what are the common milks that are found in the market? I would go over some of these. for you, at least the market that I know about. Okay. One is vitamin D or whole milk, homogenized and pasteurized milk packaged with additional vitamin D added. None of the fat has been removed prior to packaging. Okay, often 3.5% fat. That's vitamin D or whole milk, 3.5%. Okay. Low fat or skim milk. What's that? Milk, which some or nearly all the milk fat has been removed. These milks range from 2% fat to less than 0.5% fat, non-fat or skim milk. Because the body of the milk is more watery without the fat, these milks often are supplemented with whey protein, make them thicker. Condensed milk, sweetened or non-sweetened, unsweetened, whole milk with much of the water boiled away. This milk was created to serve as a concentrated form of milk and fight food poisoning, actually during the US Civil War in 1865. Now this is commonly used for a range of cooking and baking. I tell you, it speeds up a lot of cooking if you start with condensed milk rather than boil milk to make condensed milk. Okay, and then we come to whipping and heavy creams. Cream is the fat globule layer from milk, which has cream. Differences between heavy, 30%, and whipping cream, which is higher, from 36 to 40%, are primarily in the concentration of fat. Both creams can be used to make whipped cream, although the more fat, the better the resulting foam. In terms of taste, half and half is a mixture of milk with cream for a lower percent fat. Okay, it's mixed it in half. So these are the terms that people use in dairy products. Okay. Now we're going on to creams and butter. I hope this is, I fear in some sense this is like information overload if you've never seen any of this before. But you're welcome to look at this and to look more at it. But at least you hear these terms, you get used to them. Cream, that's separated from fat from raw milk. And what's left behind, skim milk. Okay, light and heavy whipping cream is about the fat content. We just went over that. Creams used in cooking serve to keeping denatured proteins from binding to each other and clotting and curdling. This happens because the globule membranes remain intact during cooking and bind to the proteins as they denature while cooking. We'll talk about this use of fat more as we go on later on. So now comes to whip it good. What do you do? Whipping cream. Keep it cool and don't overdo your whipping. If you overdo your whipping, you're going to end up with butter, which I'll get to in a moment. These foams, and we're going to talk about foams as we go on, are thick, stable cage of fat globules formed when mechanically shearing the heavy cream. And why heavy, not light? Because it's going to have much more fat content. Whipping breaks the fat into smaller pieces, which the membranes cannot fully cover. This results in partial connected crystalline I think it should be globs of fat with proteins wrapped around air bubbles. Okay, so we're actually introducing air into it. We're making a foam. So here's an up close look at whipped cream. Let's look at it. Here's air bubble. Here's the casein micelles. Here's whey protein. Okay, partially crystalline, fat globules, partially coalesced. Look like this. Okay, with air. All types of air inside. This is not the scale. Okay. And here's now a good picture of this. And I like this. This is the structure of whipped cream as determined by a scanning electron microscope. A is an overview showing the relative size and prevalence of air bubbles. Okay. That's A. That's the air bubble. And fat globules. That's F. Okay. Okay, and we have a 30 micron is the bar here showing the size. Now B is the internal structure of air bubbles, okay, showing the layer of partially coalesced fat, which has stabilized the bubble. Okay, that is now 5 microns, and it's getting, okay, and details of the partially coalesced fat layer showing the interactions of the individual fat globules. Shown here. So we have some real good idea of what's happening. Whipping cream, keep it cool and don't overdo your whipping. Warm fat oozes together and pools into one big blob. So you'd like to keep it cool, okay? No air, no foam. Overwhipped fat, while cold, forms too many contacting fat globs, and the cream turns into butter, okay? Which I happen to like butter as well as cream, but that's what you're going to get. You get butter. So we'll talk about butter. What is butter? Here's the picture of butter. Churned cream resulting in a hardened fat with most of the water expelled. Okay, this is amazing. 21 pounds, okay? Divide by 2 approximately to get kilograms, if you prefer on the order of about 9 kilograms or so. Of fresh cow's milk are needed to make 1 pound or half a kilogram of butter. So butter really requires so much. Look at the reduction going on, 21 to 1. You got that? That's butter or creams. Now, an average American consumes more than 4 pounds each year of butter. And then I want to again tell you about India. They have something called clarified butter. You can see through it. It's called ghee. And in India, clarified butter is the most eminent of all foods. In addition to being used as an ingredient in frying oil, it is the emblem of purity and ancient offering of the gods, the fuel of holy lamps and funeral pyres. Ghee, from the Sanskrit for bright, was born of necessity. Ordinary butter spoils in only 10 days in much of the country, while the clarified fat keeps 6 to 8 months. So that's why ghee came about in India. Okay, now I thought I'd go on to ice cream. Again, it's not so popular from what I can tell in China, but it's extremely popular in the West, particularly in the United States. In fact, if you ask me, one of the few foods that actually has very much United States or American on it is ice cream. So here is the saying, ice cream, you scream, we all scream for ice cream. Okay, ice cream is the result of chemical technology. Ice cream is a mixture of ice, remember that's frozen water, and partially solid milk fat, liquid, cream and sugared water, and air pockets. That's half of the volume. A lot of air is put into ice cream. Differences are in the fat and protein that creates a creaminess, the quantity of crystals of fat in water, and the protein emulsifiers that stabilize the membranes of the fat and decrease crystallization. Okay, and here are some pictures, microscopic pictures of it. Ice cream is a result of the same chemical technology. More crystals lead to less smooth and more crunchy ice. That's just not good. If you make large crystals, okay, it is not pleasant, not as pleasant as small crystals. So it's going to be very important in deciding how to make good ice cream. Whipping, emulsifiers, and sugar all influence the crystals as they freeze. To ice the cream, all one must do is create an environment colder than the freezing point of water and milk. So the challenge is to create a lower temperature than sugar water. It's a little less than 0 degrees centigrade. But the temperature of ice is warmer than the temperature needed to freeze the cream. It goes back to the 13th century Arabs knew how to create a colder than ice temperature, and they used salt. Okay, you can actually lower temperatures with salt, ice salt. Okay, this is the idea of freezing point depression. A solution of water in a solute will have a lower freezing point than pure water. And this is a result of ions interfering with the ability of water to form a hydrogen bonded network, a lattice of bonded molecules. Okay, and this was figured out first, it seems, by the Arabs, who knew how to therefore start to make something like ice cream, but not very well. So I thought, formally looking at melting point. So these are colligative property. The freezing point is influenced and due to the small amount of dissolved solids rather than the solute. Okay, this is the change in temperature. That's some constant, and that's the concentration. And so what's this all about? The more salt particles, the bigger the freezing point depression. This is how frogs and penguins can survive freezing. They're salty, okay? And it's very important because why is it the penguins can go into the Antarctica and not freeze? Right? And certain other things is often has to do with things like this, different proteins as well as salt that get into water. Now, the taste of ice cream. Overrun is a measure of the volume of air whipped into the ice cream mix. Overrun does not have to be declared in the label. Okay, so if you want to make money as an ice cream maker, you make a big amount of air because air is cheap. Okay, quality of ice creams have lower overruns than those of reduced quality. Generally, the more overrun, the lower the cost of the ice cream. You can judge the amount of overrun by the weight per unit volume, which of course is what we call density. Ice crystals form when some of the ice cream's water separates from fat and eventually develops into larger ice crystals. The result is a grainy textured ice cream. So long as water remains trapped in an emulsion with fat in ice cream, the original ice crystals do not get larger. To protect ice cream from developing large crystals, do not melt and refreeze the ice cream. This is a big mistake. If you have ice cream and you melt it and then you stick it back into the freezer, you've just made a mistake. You don't want to do that because you're going to get big ice crystals. Do not store ice cream well below freezing for a long period of time. So more about ice cream. 3 major components. The ice crystals form from water molecules as the mix freezes, and it gives ice cream its solidity. They're its backbone, and their size determines whether it's fine, smooth, or coarse and grainy, but they account only for a fraction of the volume. Concentrated cream is what is left of the mix when the ice crystals form. Thanks to all the dissolved sugar, about 1/5 of the water in the mix remains unfrozen. Okay, the result is a very thick fluid that's about equal portions of liquid water, milk fat, milk proteins, and sugar. That's why it's creamy. This fluid coats each of the many millions of ice crystals and sticks them together, but not too strongly. That's why it tastes creamy. 3, air cells are trapped into the ice mixture when it is agitated during freezing. They interrupt and weaken the matrix of ice crystals and cream, making the matrix lighter and easier to scoop and bite into. The air cells inflate the volume of the ice cream over the volume of the original mix. The increase is what I called overrun, and in a fluffy ice cream can be as much as 100%. That is, the final ice cream volume is half mix and half air. The lower the overrun, the denser the ice cream, the richer it is. Okay. Now, interesting, just some history about ice cream. America transformed ice cream into a food for the masses. As I mentioned, it started earlier than that, but it was really these inventions that mattered. Ice cream making was an awkward small batch procedure until 1843, when Nancy Johnson of Philadelphia patented a freezer consisting of a large bucket for brine, that's salt water, and a sealed cylinder containing the ice cream mix and a mixing blade whose shaft protruded from the top and could be cranked continuously. 5 years later, William G. Young of Baltimore modified Johnson's design to make the mix container rotate in the brine for more efficient cooling. The Johnson-Young freezer allowed large quantities of fine textured ice cream to be made with a simple, steady mechanical action. So people had to crank away and make ice cream. Today, Americans eat substantially more ice cream than Europeans do, nearly 20 quarts or liters per person every year. Ice cream, very popular. Okay, I thought I'd go through further about the making of ice cream. One of the labs I have when I teach my course is I have people make ice cream using dry ice. It's also made using liquid nitrogen, but that's not as much available. So what's going on? On March 13th, 1943, the New York Times newspaper reported that American flyers stationed in Britain, after all, it's World War II, had discovered an ingenious way of making ice cream while on duty. A story titled "Flying Fortress Double as Ice Cream Freezers" disclosed that the airmen placed prepared ice cream mixture in a large can and anchored it to the rear gunner's compartment of this airplane. It is well shaken up and nicely frozen by flying over enemy territory at high altitudes. It's, after all, very cold in the sky. These days, a popular, spectacular, and effective method among chemistry teachers is to freeze the mix in an open bowl with a gallon or two of liquid nitrogen. Okay, and when the liquid nitrogen is stirred in, it boils, bubbles, and chills the mixture almost instantly throughout, a combination that makes a very smooth and initially very cold ice cream. So that's very popular. I tell you, dry ice is much easier to work with, and this is very available in a number of places. Now I thought I would coming for me. I don't think I'm ever going to make it past more than about 45 minutes, but here we go. Old-fashioned cheese making. I now want to talk about cheese. It is acidifying milk, essentially lowering its pH, and it causes the milk proteins, like casein, to unwind and unfold in a process known as protein denaturing. The milk takes on a curdled appearance from the lumps of proteins that are binding one another, and you need to add some acid. And as I mentioned to you, the acid can be lemon juice, that's citric acid, or vinegar, acetic acid. Lime juice is even more citric acid. Another approach is adding a lactose digesting bacteria that makes lactic acid, another acid. These bacterial cultures are used in the preparation of yogurt, sour cream, and many other cultured milk products. So that's where yogurt's coming from. And now that we understand this, it is a lactose digesting bacteria. We understand now why yogurt is so low in lactose and therefore is so much favored by people who have some lactose intolerance. And it's all making, I hope, some chemical sense to you. So here's now modern cheese making. How is that done? The curdling of milk by this particular enzyme, okay, called a rennet enzyme called chymosin, okay, are kept separate from each other by electrically charged micelle components that repel each other. It trims away these charged kappa cases, and the now uncharged micelles bond to each other to form a continuous meshwork, which is what's on the right. And the liquid milk coagulates into a moist solid. And that's the making of cheese. That takes time. So people spend a long time making cheese. Okay. And I thought I would now share with you what's going on about cheese in China and elsewhere. Okay. In 2019, the per capita consumption of cheese in Northeast Asia in kilograms. Okay. This is per capita consumption of a year, per year. Okay, South Korea, 3.14 kilograms. Japan, 2.56 kilograms. China, 0.51 kilograms. China has something like 6 times less use of cheese than South Korea. China doesn't much do anything with cheese. Okay, very hard to find cheese. Yet, but again, those people who have a feeling for it, you can't really make pizza without basically putting cheese melted on some type of dough. And so, again, cheese is very much known in the West, okay? But not so much in China. This is interesting because this represents actually a new opportunity for China to change its cuisine if it wants to. And I would now want to just compare the dairy consumption patterns in China and the US. And I thought you'd find this fun to see. What goes on? Milk, baby formulas, and yogurt are the 3 top most consumed dairies by volume. This is by volume, accounting for 39.3% is milk, 27.6% is powdered milk, the baby formula, and 23.6% is yogurt. Add these numbers up and you'll see that only about 10% is something else. Okay, that's what's going on in China. And now ask yourself again, based on volume, where is dairy being used in the United States? And the answer is cheese accounts for the largest share of per capita U.S. dairy product consumption. And I think you'll find that surprising. Okay. Cheese, however, as you know, involves the action of bacteria, and cheese can often have different tastes, and it's a matter of getting used to it or acquiring a taste for it. And so if you've never tasted cheese and you taste it for the first time, you'll say it's rotten, it's no good. Like you will say about most fermented materials. People do not like beer the first time they have beer. People do not like sauerkraut the first time, but they get used to it. All these are fermented, or natto in Japan. Okay. Comparison of plant-based milks to whole cow's milk. I thought this would be interesting. And now I'm coming towards the end of what I want to present to you. I think there's going to be a new change in the way foods are made as we go on. Foods have changed in the past, and I think they're going to continue to change in the future. And I want to argue why this is so. Okay? And we know now that people are very interested in plant-based meats compared to animal meats. What about plant-based milks? What do we know about that? They've been a while around. Let me show you. Here we go. Here's whole milk. This is soy, coconut, almond, and rice for fun. And all these are milks, okay? There's oat, there's other things, but this is very common. Let's compare them. First of all, you'll find in terms of energy, okay, that whole milk, I think, is the winner, pretty much, okay? It beats out the others. So if you want to talk about calories, you get more calories from whole milk. Some people don't want calories, right? Want to keep thin, not get fat. So these actually are ways to avoid those calories. Interesting. What about proteins? Well, soy rivals whole milk, okay? But the others are really down in proteins. Look at that. Coconut hardly has any protein in it, okay? Carbohydrates, we see what that's like. Again, this is reducing the calorie value, bringing it down. Here's the total fat, half as much here. Milk's much fattier, see? Okay. Fiber. Here's sugars. Milk itself is sweeter. Now, this is, of course, unsweetened, so people add sweetening often to things like soy, okay, or coconut. And I'm showing you, for in terms of vitamins, okay, this turns out to be pretty similar. And I don't know what that is. I can't get rid of it. Let's see if I can get it. Calcium. I wanted to compare calcium to you because here it is. Milk contains calcium, but if you look, these are down. They're but not all. Almonds are even higher actually in calcium. This is in milligrams. Okay, and this is all for 1 cup. Is what we're talking about here. That's one thing. That's one aspect. What other aspect is there? This may well be my last slide. Let's see if I can do that. Okay, let's try. Okay. We're coming right to the end. So this is for my course, Chemistry in the Kitchen at Stanford. This is cooking with foam. Make milk foam, which can be used as a topping for drinks such as coffee. And I don't know, here are the instructions. And I actually, in my course, I have everybody do something as we talk about it and then eat what they do. So you pour the milk into a small jar that has a tight-fitting lid. Fill your jar with as much milk as you can, okay, as you normally use in your coffee, but no more than halfway full, so that there's room to make foam. So it's half filled. Try whole milk and compare it against 2% and 1% milk. Remember, whole milk is 3.5% approximately. Here's 2% or 1%. And with the lid screwed on, shake the jar as hard as you can until the milk is froth and has roughly doubled in volume. That's 30 to 60 seconds, easy to do. Now, put it into a microwave, but make sure you take any metal lid off. You don't want to metal into a microwave. And for about 30 seconds, what will happen? You really will tend now to cook a little bit of this, and you will get a foam that stays there. And time how long it takes the foam to collapse to half its height. You can do that with your smartphone or with a stopwatch. And then my question to my class was, what do you conclude about which type of milk is more successful in producing a foam? Do you think foams are best made by whole milk, by 2% milk, or 1% milk, or for that matter, even skim milk? What makes the most long-lasting foam, and why? Okay, and then I thought we could discuss that some, but I thought rather than trying to do that, and I can't see you well, I just go on and give you an explanation. Oh, this is sort of out of order. So do I have an explanation? Aha, these are sort of out of order. Okay, I'll come back. So my cooking class discovered that skim milk makes a more long-lasting foam than whole milk. It really, the less fat, the better. Moreover, hot milk foams better than cold milk. Okay, and of course the question is why? Why is this so? And so I wanted to give you some idea. Here's a simple explanation. Steam is created when water vapor and air are forced into milk via the steam wand of an espresso machine, okay? But it's not enough that air is introduced. The milk also needs to be heated for that foam to stick around. You know how an egg starts to get solid and opaque in a hot skillet? The same things that cause these changes in an egg are what happens in milk when you heat and steam it. Milk proteins, which start out bundled like little balls of yarn, denature, they unfold when exposed to heat, allowing them to interact with each other more strongly. So not only will acid cause unfolding, but heat will cause unfolding. The proteins chains in milk are polar. One end of the chain is hydrophilic, loves water. The other end is hydrophobic, repels by water. Because milk is mostly made of water, as soon as these proteins unfold, exposing their ends, the hydrophobic ends try to get out of the water. They immediately try to get as far from the water as possible. If you were to look at a single tiny bubble in a cup of foamed milk, you'd see that the hydrophobic ends of milk proteins are all pointed inwards towards the water-free interior of the bubble, while the hydrophilic ends stay put in the aqueous environment the bubbles are suspended in. This structure keeps the air bubbles intact for a long time after the steaming process. And so we get to see what happens. So far, we understand why heating helps, but we still didn't get the idea what the fat content does. So let's go on. Hydrophilic ends are also attracted to fat particles. Okay, they love each other. Just as they allow air and water to form a stable mixture to foam, they allow milk fat and water to form a stable fat and water emulsion in a carton of milk. The more fat you have in the milk, the more viscous it feels. So what does this mean for foaming? The absence of milk fat in skim milk means that those proteins wind up orienting themselves with their hydrophobic ends pointed inwards towards the air bubbles being injected into liquid in order to get away from the water as much as possible. And this regular structure helps strengthen the walls of the bubbles and prevents its collapse. If you add foam, add fat, they don't do that. They get capped with fat, and this process therefore doesn't form a strong set of walls, and so the foam collapses. Now, the next fact is very interesting, but a drier, sturdier foam does not mean a better tasting foam. So making foam from skim milk will easily get you more of foam, but this foam may not be as pleasurable as making it from like 1 or 2% milk. Okay, so if I can, I will get to that. I want to go back to something else that I skipped. I want to talk about the environmental footprints of dairy and plant-based milks. I think you'll find this very interesting. These are the impacts are measured per liter of milk. So we're going to talk about per liter of milk. And okay, what do we see? Dairy milk, in terms of land use, it takes up 8.95 square meters. What about soy milk? It takes up 0.66 meters. That seems to me to be more than a factor of 10 difference. Okay? And you see what's going on. All the plants require much less land use. What about greenhouse gas emissions? Dairy milk involves cows, And look, 3.15 kilograms. And soy milk, 0.98 kilograms, etc. when you go through it all. Almonds the winner here. What about fresh water use? Dairy milk requires a lot of fresh water. Soy milk, very little. And we got about eutrophication, but I hope you're getting the idea. Again, soy milk's the winner. It is very, very likely that we, as we learn to add things, not milliming, okay, we talked about that's a disaster, but as we learn to add the right things, we're going to make new types of plant-based milk that'll taste very much like dairy milk and have its right properties, and people will be very happy with it and dispense with the use of animals to make it. Okay, now let me go on to the ending. And the ending I wanted to share with you is this conclusion. A little bit of chemical understanding means that you will never look at food again in the same way. I hope this discussion I've given you about dairy has helped you see all the things that come from milk and how a little bit of chemical understanding allows you to understand very much what its uses in cooking and what it's like to have. Now, with this, I'm going to try. Come on. Oh, do I have to turn this off? Can't do that. I want to stop the screen share, and I'm trying very hard to do that. Well, I'm not sure it knows how to do that as long as this is on. I'm stuck. Anybody knows how to escape this? Great. I think I'm stuck. I don't know.
I think the button is at the bottom of your screen.
Yeah, but I don't seem to be able to get there.
I think you need to close your PowerPoint first, I think. And then
Let's try escape. That
yeah,
may
yeah.
do it. Okay, that will do it. And now it allows me to hopefully
Okay.
let's see where we are. Okay.
Okay.
Okay. I'm trying very hard to turn this off.
Oh,
What if I
okay.
click this off? Oh, there we are. Good. And so
Yeah.
now I can see you. Okay.
Okay.
And,
Oh,
we
okay.
have 51 attendees, which is quite amazing. Okay, great. Thank you.
Oh, okay, great. Let's thank the Professor Zias for his wonderful report. I believe our students have learned a lot about the dairy products, like the milk, like the ice cream and the cheese and so on. Because it is a great opportunity for our students to communicate with you. Please give us more time to enter the question and answer part, okay?
Oh, certainly. First, I want to give a call out to Wei Hong Tan, who I see. Oh, I'm so pleased. Glad you could join.
Our students, do you have some questions? Please raise your hand if you need to ask a question. Oh, okay.
Thank you, Professor, for giving such an interesting and exciting lecture about dairy. I have some questions for you. As what you said, for the yogurt, it is low in lactose but high in some nutrients. I want to know whether or not there are some chemical procedures that cause the yogurts to have low in lactose. Could you please answer the question?
You want to know if there's a chemical procedure to cause yogurt to do what now, too?
Because pardon, I didn't hear what you said. I'm sorry.
I'm not sure. I'm sorry. I'm just having trouble understanding the question. The bacteria eats the lactose, which is good, so it cuts it down. It doesn't do much else. And the bacteria, we're not bothered by eating it. And as you know, there's all types of probiotics that you can do too, that are related, that are good for us. So yogurt's very, very popular. And you wanted to know more about yogurt in terms of? I'm sorry, I'm just not understanding the question.
I just want to know why the yogurt is low in lactose. And I think you have already answered my questions. Thank you.
It's because the lactose is being eaten by the bacteria. That's why. That's actually why. And when it eats it, part of what it makes is lactic acid, and that makes it taste sour. So yogurt tends to be on not the sweet side, the sour side. Okay.
Yeah. Thank you.
And of course, we get used to this. We find that it can be fine. And then you can add sugar and overcome the sourness too. People do. People add all types of fruit to the yogurt. Fruit sugars or fruit itself, right?
Yeah.
But plain yogurt alone, it tends to be sour. And you see why. It's to me so, I don't know, personally, so fascinating that a little bit of understanding about the chemistry of what's going on really is affecting your life in what you experience in food. All of us, must eat. Okay. Some of us, eat to live, others live to eat, but food's very important. And then you see that chemistry is very much involved in it.
Okay, thank you. And that's my questions.
Thank you. I understand.
Okay. Any other questions? Any other questions?
Okay, Professor, thank you for your excellent report. And I have two questions for you. And first, you mentioned the melamine, which is used to improve nitrogen in the milk. Is there any fast and easy technology or method to detect trace amounts of melamine in milk?
Yes, people now check for melamine. And I would need to explain to you, for example, how a mass spectrometer works. Is this something you've covered in your class or not? Anyways, you can take droplets and make them into the gas phase, gas molecules, make them ionized, and then depending upon their mass and their charge, they'll be deflected different amounts. And this allows the one with a mass spectrometer to make a chemical analysis. And we can also even look at fragments. And so we can know whether or not we have melamine. That's one way. There's other things called chromatography that you can do in which you separate things depending on how sticky they are to something else, a column that they go through of other material. So there's many neat chemistry techniques to be able to check for melamine. Today, people check for melamine in milk. They don't want melamine. That's deadly, as you heard. No good, right?
Yeah.
On the other hand, people have been adding things to milk all the time. For example, as I mentioned to you, people are always adding vitamin D to milk. Okay, good for us, etc., and other things. So,
yes.
It just was an unfortunate choice that was not understood when it was done.
Yeah, so it is important to detect melamine in milk. It is good health for us. And then the second question is the whole milk and the skim milk, which is fat has been removed. Which of them better for us, especially for young people?
Well, what's better for us? They're both fine for you. It depends whether or not you want the fat. Now, skim milk to me is more watery because of the removing of the fat. I don't happen to like the taste of skim milk as much as I like that of whole milk, but you can use it, and people do. And as I told you, it more easily makes a foam, and we saw that. And you can try in the lab and prove it to be so. So people now, at least where I live, sell milk with different percentages of fat in it. 1% milk and 2% milk, and people get all excited about this in general. But you get the idea.
Yes, in real life, I prefer to choose the whole milk. The taste of the whole milk is better than the skim milk.
I think since you're just primarily removing the fat from milk, you're not changing many of the other things, that they both have very good nutritional value if you wanted to.
Okay, thank you, Professor.
As does soy milk. Again, I showed you that, which has less fat. Again, another way. Very okay. I appreciate this opportunity to talk to you all. I wish it was possible for me to come visit China again easily, and I'm waiting for a time when it's easy for me to do that again. I want to. I've been to Hefei and I've enjoyed it, and I'm envious of you at USTC. Great university that you're at. And so I thank you so much for giving me this opportunity. Professor Fang Simin, thank you.
Yeah, thank you for to give us the lecture. We are so honored to invite you to give us the lecture. And last, I want to say you have the great academic achievement and the admirable charisma. And thank you again to give us the lecture. And wish everybody here and online have a good mood and stay healthy every day. Thank you.
Thank you all.
Okay, bye-bye. Bye-bye. Bye-bye.
Good to see you.
Cheers.
See you.
Bye bye.
Bye-bye.